All right, everyone. Take a good look at this image. You see a soccer ball right here on the field. And you see this big glowing blue arrow shooting diagonally into the air. That arrow, that is the total force of the kick. One single push from the player's foot. Now, here's the question I want you to sit with for a moment. When the player kicks the ball at this angle, not straight forward, not straight up, but diagonally, where does the energy go? Think about it. The ball doesn't just move in one direction. It moves forward across the grass, and it rises up into the air. So one single kick is doing two jobs at the same time. Look at the image again. Notice those two arrows that split off from the blue one. The orange arrow pointing forward along the ground, that is the horizontal component. The green arrow pointing straight up, that is the vertical component. Now, see that angle label, 45 degrees? At 45 degrees, something beautiful happens. The horizontal and vertical components are equal. Half the force goes forward, half the force goes up, perfectly balanced. But what if the angle changes? What if the player kicks at a shallower angle, almost flat to the ground? Then most of the energy goes horizontal. The ball stays low and travels fast. What if the player kicks almost straight up? Then most of the energy goes vertical. The ball shoots high but barely moves forward. This is the core idea. One diagonal force splits into two perpendicular pieces. And the functions that measure exactly how much goes horizontal and how much goes vertical, those are cosine and sine. Let's find out exactly how they do that.
Now we're going to make this really physical, really tangible. I want you to imagine a rigid metal rod, a straight stick, fixed at the origin of a graph. That rod represents our force vector. Its length represents the strength of the force. Now, directly above this rod, we place a very special light source. Not a regular torch, and this is important. A regular torch spreads light in a cone shape. That cone distorts shadows. We don't want distortion. We want perfect mathematics. So we use a collimated light source, one that emits perfectly parallel rays of light. Think of it like the sun, very far away. The rays come straight down, perfectly vertical. Look at the left side of the image. The rod is tilted at 30 degrees. The parallel light from above hits the rod and casts a shadow on the x-axis. That shadow, that horizontal stripe on the floor, that is the cosine. Read the label. Cosine of 30 degrees is approximately 0.866. That means 86.6% of the rod's total length is contributing to horizontal movement. 86.6%, almost the full length, because 30 degrees is a shallow angle, mostly horizontal. Now look at the right side. Same rod, same light source, but now the rod is tilted to 60 degrees. Much steeper now. The shadow on the floor is shorter, much shorter. Read the label. Cosine of 60 degrees equals 0.5. Only 50% of the rod's length becomes horizontal shadow. Do you feel the logic here? As the rod tilts more steeply upward, the horizontal shadow shrinks. As the rod tilts more flat, the horizontal shadow grows to match the full rod length. Cosine is the horizontal shadow ratio. Cosine tells you, of this total force, how much acts left or right, horizontally. Now, what about the force acting up and down, vertically? That's the next image. Keep watching. Perfect. Now we flip the light source. In the previous image, the light came from above, shining straight down onto the floor. That gave us the horizontal shadow. That gave us the cosine. Now look at this image.
the light source, that little projector, has moved to the left side of the frame. It's no longer shining downward, it's shining horizontally, perfectly sideways, from left to right. The parallel rays hit our rod at 30 degrees, and this time the shadow falls on the vertical wall. The y-axis. The wall. See that green vertical bar on the y-axis? That glowing green shadow? That is the sine. Read the label. Sine of 30 degrees equals 0.5. Half. Exactly 50% of the rod's length becomes a vertical shadow on the wall. Now let's connect this back to image 2. At 30 degrees, we just saw that cosine 30 degrees is about 0.866. The horizontal shadow is 86.6%. And sine 30 degrees is 0.5. The vertical shadow is 50%. Why does the horizontal shadow come out bigger than the vertical shadow at 30 degrees? Because 30 degrees is a shallow angle. The rod is mostly lying flat. So it casts a big shadow on the floor and a small shadow on the wall. Simple physical reasoning, and it matches the mathematics perfectly. Sine is the vertical shadow ratio. Sine tells you, of this total force, how much acts up or down, vertically. Overhead light gives cosine, horizontal shadow. Side light gives sine, vertical shadow. Lock that in. That is the physical meaning of these two functions.
This image is where everything connects. Watch carefully. We have a unit vector, a rod of length exactly 1, pinned at the origin. And we're going to slowly rotate it from 0 degrees all the way up to 90 degrees. Look at the bottom of the image, the orange bar along the x-axis. That's the horizontal shadow. That's the cosine. Look at the left side, the green bar along the y-axis. That's the vertical shadow. That's the sine. Now let's read the values angle by angle. At 0 degrees, the rod is completely flat, lying on the x-axis. The orange horizontal shadow covers the entire x-axis from 0 to 1. Cosine of 0 degrees equals 1. 100% horizontal. The green vertical shadow? It doesn't exist. 0 height on the wall. Sine of 0 degrees equals 0. Now the rod starts tilting. At 30 degrees, we just studied this. Energy is being traded. What the horizontal loses, the vertical gains. At every single angle, there is a perfect mathematical balance between these two values. And there's one more thing to notice before we move on. We've been using a rod of length 1, a unit vector. Why length 1 specifically? Why not length 4 or length 5? That is exactly the question the next image will answer.
This final image is the one that ties everything together philosophically. It answers the question, does the size of our force vector change the sine and cosine values? Look at the diagram. We have 3 circles centered at the same origin. The small gold circle, radius 1 centimeter. The medium blue circle, radius 4 centimeters. The large red circle, radius 5 centimeters. Now, one single line, our vector, is drawn from the origin at 30 degrees. This line cuts through all 3 circles. For each circle, we drop a vertical line down from the point where our 30-degree ray hits the circle. That gives us 3 different triangles, same angle, different sizes. Now let's measure the vertical sides. For the small circle, radius 1, the vertical side y1 equals 0.5 centimeters. For the medium circle, radius 4, the vertical side y2 equals 2 centimeters. For the large circle, radius 5, the vertical side y3 equals 2.5 centimeters. They're all different numbers, but now divide each vertical side by its circle's radius. For r equals 1, we get 0.5 divided by 1,
equals 0.5. For r equals 4, we get 2 divided by 4 equals 0.5. For r equals 5, we get 2.5 divided by 5 equals 0.5. Every single ratio is exactly 0.5. The size of the circle doesn't matter. The size of the force doesn't matter. At 30 degrees, the vertical shadow will always be exactly 50% of the total length. This is the deep truth behind trigonometry. Sine and cosine are ratios. They are properties of the angle itself, not of the size. Now look at the gold circle labeled normalized radius. When the radius is 1, the division step disappears entirely, because anything divided by 1 is just itself. So sine 30 degrees equals y divided by r equals y divided by 1 equals y. The y coordinate is the sine value, directly, no calculation needed. This is why mathematicians and physicists standardize the unit circle, a circle of radius 1. It simplifies every single calculation. The coordinates of any point on the unit circle directly give you cosine and sine. X equals cosine of the angle, y equals sine of the angle. So let's bring everything together now.
We started with a soccer player kicking a ball, one single diagonal force. We saw that force split into two perpendicular parts, horizontal and vertical. We used a collimated light shining from above to cast a horizontal shadow. That shadow is cosine. We used a collimated light shining from the side to cast a vertical shadow. That shadow is sine. We rotated our vector from 0 degrees to 90 degrees and watched the shadows trade places. Cosine starts at 1 and shrinks. Sine starts at 0 and grows. At 45 degrees, they meet and are equal. And finally, we proved that the ratio, sine or cosine, never changes with size. Whether the force is 1 Newton or 1,000 newtons, at 30 degrees, 50% is always vertical. That's why we normalize. That's why the unit circle is the standard. Sine and cosine are not abstract memorization. They are shadow ratios. They are force filters. They are the geometry of direction itself. And now you know exactly what they mean. Thanks for learning with us. Subscribe, share, and comment.